Okay, in this lesson, we're going to talk about Ohm's law, resistance. So let's talk about what Ohm's law is. Ohm's law states that for ohmic conductors, that means for conductors that obey this law, we call this ohmic conductors. Now, ohmic conductors follows Ohm's law. Ohm's law states that when the physical conditions are constant, physical conditions means the temperature, for example, as well as the length, as well as the factors that affects the physical state of it remains constant, then the potential difference across the conductor is directly related, is proportional. The potential difference is directly proportional to the current flowing through it. Okay, so essentially what it's trying to say is this: for any ohmic conductor, the potential difference across that conductor will be directly proportional to the current. So for example, if you have a piece of wire, okay, assuming that the electrons or the conventional current is flowing through it. So if this is a piece of ohmic conductor, then if you were to measure using a voltmeter, if you were to measure the potential difference across it, you'll realize that there is a relationship between the current flowing through it and the potential difference across it. In fact, the relationship is directly proportional, okay, which means that if my current increases, my potential difference will also increase. If my current reduces, then my potential difference will also decrease. So in mathematics, we know that there must be a constant that is affecting these two. Okay, so what is this constant? This constant for ohmic conductors only, there is a ratio. The ratio that governs the relationship between potential difference and current is known as resistance. So resistance is actually a ratio that is between potential difference and current. And this applies only to ohmic conductors. Ohmic conductors are conductors where the potential difference is directly proportional to the current when the physical conditions remain the same. Okay, so repeat again, resistance is a ratio, okay? It is a mathematical ratio that shows you the relationship between potential difference and the current across any ohmic conductors. Now let me show you a simulation. So you see here, there is a simulation where there are 3 cells. Each cell is 1.5 volt. They are in series. So in total, the total EMF is 4.5 volt, all right? Now, 4.5 volt is the potential difference across this piece of conductor in red as well, all right? So now, as you can tell, the potential difference and the current is directly proportional, and there is a ratio R. So as I increase the potential difference, you realize that my current becomes, okay, so let's change. So as I increase the potential difference, can you see? The current also increases. As I decrease the number of EMF, the current also reduces, okay? So therefore, you realize that if the ratio doesn't change, then as V increase, current also increase. As V decrease, current also decrease. So there is a direct proportionality, okay? Now you can adjust the resistance if you take another piece of wire or you take another piece of conductor. Okay, if you were to reduce the ratio, likewise, as V increase, I will also increase. So the more EMF there is, the larger the current. The lesser the potential difference or the EMF, the smaller the current. So that is essentially what Ohm's law is referring to. So therefore, resistance is a ratio. Resistance is a ratio, and the ratio between two quantities, V and I. All right. So for ohmic conductors, this ratio will not change. Okay, so for ohmic conductors, let me just write it. So for ohmic conductors, R remains constant. Okay, so if you don't change the physical conditions, then the resistance remain the same. Okay, now, but sometimes you might want to change the resistance. Then you got to tweak the physical conditions a little bit. Now, there are some factors that will affect resistance. that will affect this ratio. Number one, the length of the wire. If you change the length, you're changing the physical conditions, right? Okay, so length, if you increase the length, you will expect the ratio R, the resistance, to increase as well. Okay, just take note, just like when you're running 2.4 kilometers versus you're running 200 meters. If you run 200 meters, it's going to be easier, right? If you run a longer distance, it's going to be tougher. So therefore, the longer the wire, the higher the resistance. Okay, so remember, resistance is similar to the obstruction in the water system. So the higher the resistance, the slower the current flows. The second thing that affects it is the cross-sectional area. Cross-sectional area. Number two, the cross-sectional area of the wire affects it as well. So the thicker the wire, the lower the resistance. Okay, so I'll think about a very narrow road versus the expressway. The expressway is wider, allows current to flow easily, so therefore resistance drops. But if the road is narrow and winding, it's very difficult to travel, then it's going to slow down the current a lot. The third factor is the temperature of the wire. Okay, the higher the temperature of the wire, the hotter the wire, the higher the resistance. Why? Molecules in the wire vibrate faster, and this will slow down the electron flow, okay, because of the greater movement of the atoms. The fourth factor is the material of the wire, which is known as the resistivity of the wire. Now, this is entirely dependent on the material. Some wires are of a higher conductivity, some are of a lower conductivity. So therefore, the higher the resistivity of the wire, the resistance increase as well. Okay, so therefore, there are four factors. So if you were to take note, there are three that are directly proportional, which is length, temperature, and resistivity. So the higher, the longer the length, the hotter the wire, and the higher the resistivity, which is the material itself, the higher the resistance. Okay, so therefore you can actually use this to form a relationship. So the resistance can be found using V over I. There's one way to find, because resistance is the ratio between the potential difference and the current. But resistance can also be found in terms of the factors. So the resistance is directly proportional to the length, so it must be the numerator. Now, temperature, assuming temperature is constant, we are deriving this formula. Now, resistivity is represented by the Greek word rho, which is similar to density. The resistivity, so this is the resistivity. Resistivity and the length must be in the numerator as it is directly proportional. Okay, now there is one that must be in the numerator because of the inverse relationship, right? The thicker the wire, the lower the resistance. So therefore, cross-sectional area will be here. So there are two formulas that allow you to find the resistance. Again, resistance is a ratio between potential difference and current. And if the physical conditions remain the same, resistance should not change if it is an ohmic conductor. Okay? So again, temperature is constant if you want to use the second formula below. Okay? Now, therefore, I can adjust the resistance if I change the length and the area. So therefore, when you want to make resistors, there are two types. You have the fixed resistor. Now, fixed resistors means that the resistance is fixed. You cannot adjust it. You cannot adjust the length. You cannot adjust the cross-sectional area. So this provides a fixed resistance, okay? Or you can, this is the first example. And the second type of resistor would be the variable resistor. So a variable resistor allows you to vary the resistance by changing its length or cross-sectional area. Usually by length is easier, by changing the length, area, or the material. Okay, so there are two types. So let me bring you to the relationship here. So as mentioned, if temperature is constant, then the resistance of a conductor can be changed by changing the material, which is resistivity, making it longer, or making it thinner or thicker. Let's say we just change one of it. So if I have something that is of a higher resistivity, you realize that the material provides a higher resistance. If I use another material of a lower resistivity, the resistance is naturally smaller. Okay? Now, if I were to change the length, remember, the longer the length, the more resistance there will be. Therefore, when you're charging your phone, don't use a long wire. Use a shorter wire so that you allow the current to move quickly, therefore allowing the energy to be transferred to your phone faster. So can you see, the longer the wire, the more resistance it provides. The shorter the length, the lower the resistance. Okay, and finally, area, the cross-sectional area. So you think about the expressway versus a small lane. The expressway is so much easier for the charges to flow through. So when I have a thicker wire, my resistance drops. If I have a thin wire, it's going to make it very difficult for the charges to flow through. Okay, so this is how the factors come together to affect the resistance in a wire. So again, resistance is a ratio, and this ratio can be changed by changing some of the factors. Okay, but for ohmic conductors, if the physical conditions remain the same, then the resistance should always remain the same. Okay, now let's take a look at how to calculate resistance in a series and parallel circuit. Now, the word total means that you consider one or more resistors. Okay, so what do we do if there are more than one resistor? How do we calculate the total resistance of that particular circuit? Now remember, resistance refers to the ratio. So we want to find the effective ratio between V and I. Okay, so let's say, for example, we have a series circuit made up of two resistors. Okay, now this is a series circuit because the charges has only one path to flow through. It will flow through R1, R2 and go back home. Okay, so the total resistance or the effective resistance is equals to R1 plus R2, etc. in a series circuit. So in a series circuit, it's quite straightforward. So an example would be if you have 3 ohm connected in series to 2 ohm, okay, then the effective resistance of this circuit would be simply 3 plus 2, 5 ohm. Okay, so 5 ohm tells you the ratio between the total potential difference and the total current coming out of the cell. So example, if this is the EMF of, let's say this is the EMF and this is the current that's coming out, then 5 ohm tells you the ratio between the potential difference, the EMF and the current that's flowing through the entire circuit. That is the meaning of ratio. Okay, now let's take a look at how to calculate the total effective resistance in a parallel circuit. Okay, so in a parallel circuit, the charges has more than one path to go through. The charges can either flow through R1 or it can flow through R2. In a parallel circuit, the total resistance is calculated in terms of fractions. So 1 over the effective resistance or the total resistance will be equals to the fraction 1 over R1 plus 1 over R2, etc. Okay, so this is the formula for parallel circuits. So let's take a look at an example. So if this is 4 ohm and let's say this is 2 ohm, right? Now how do we find the effective resistance? We simply take 1 over R1, which is 1 over 4, plus 1 over R2, which is 1 over 2. This will give me 3 over 4. Okay, but this is not the answer because we have to invert the formula. So effective resistance is therefore 4 over 3, but we do not leave it in fraction. Leave it to 3SF, we get 1.67 ohm. Now again, this is the ratio between, this is the total ratio that is between the EMF of the entire circuit versus the total current coming out of the cell. So 1.67 ohm is the ratio between the EMF and the current coming out from the cell. That is how you understand total effective resistance. Okay, and you realize when you place resistors in parallel, the effective resistance becomes smaller and smaller. Smaller than the number will always be lower in parallel, will always be smaller than the smallest value. Okay, that's one